Hello everyone, my name is Unnikrishnan. I'm a PhD student at the Astronomical Observatory of Jagiellonian University in Poland. My research interests include galaxy clustering and its dependence on galaxy properties. Uh, now, I would like to share the results from a recent work of me and my collaborators. That is a tracing galaxy environment using Mach correlation function in GAMA. This work has been recently accepted in A&A, and here is the archive ID for it. Okay. So it's the outline of the talk. After explaining the motivation behind the work, I'll discuss about the tools that we have used, and then we'll go to the data, and then we'll see the results and the conclusions. We know that our universe on a large scale is in the form of a giant network of galaxies, and which has structures like nodes where there are many galaxies living together, then filaments, walls, and even voids where there are less number of galaxies. Now, what do we know about the galaxy formation and evolution? From that, we believe that the galaxies live in dark matter halos, just like how you can see in the sketch. Then the galaxy properties are majorly defined by the properties of the dark matter halo in which those galaxies live. And we have also observed that the properties of dark matter halo correlate with the environment in which they live. And these correlations prompt a correlation between the galaxy properties and the environment. So better insights into the environmental dependence of galaxy properties give us better constraints on the galaxy formation and evolution models. Uh, in the past, people have widely used a tool called the galaxy two-point correlation function to study the environmental dependence of galaxy properties. So, because by environment we mean the the number density of the region in which the galaxy live in, and basically two-point correlation function quantifies the clustering of galaxies, and this clustering is related to the environment. When you have more clustering, which means that it is in a high it's in a more denser environment. And a few words about the correlation function. It is defined as the excess probability of observing a galaxy pair separated by a distance r over the random distribution. On a short note, how do we use it? Well, the greater the value of the correlation function at a particular scale, the greater is the strength of the clustering at that scale. And we have observed that the two-point correlation function psi of r, where r is the separation, is follows a power law with r0 as one very important parameter which quantifies the clustering of a sample. That is, like, if you have two different galaxy samples and you want to compare like which galaxy sample exhibits more clustering than the other, you just need to compute the correlation functions and compare their strength. If you have a stronger clustering, that then your correlation function will show a higher amplitude than the other. But in practice, when we use the redshift as redshift to estimate the distance between the galaxies, uh, the this can be affected by the redshift space distortions, um, in that is caused due to the peculiar velocity of galaxies in clusters. So to avoid that, we project our correlation function, and then that's called the projected correlation function. Uh, then in practice in literature, we'll see the projected correlation function majorly uh, than the no, normal correlation function, where omega p of rp you will see mostly than this. So in the past, two-point correlation function has been widely used to study the uh, dependence of correlation function on, or the dependence on of clustering on galaxy properties. For example, in this work by Sahavi et al., they have used the correlation functions to study how the clustering depends on the R band absolute magnitude, where the red one that represents the uh, most luminous galaxy sample, and the luminosity reduces as it goes down, and we can clearly see that the luminous galaxy sample exhibits more clustering than the less luminous galaxies. They have also used color to do the same analysis and have observed that the redder set of galaxies exhibit more clustering than bluer ones. In another work by Durkalets et al., they have used stellar mass. They have found that the clustering also depends on stellar mass. And for example, here you can see the red one, that is the most massive galaxy sample, which shows a stronger clustering than the less massive galaxies. So all these results tells us that the galaxy properties, like for example here the magnitude, color, and stellar mass, they all affect the clustering, which means they all depend on the environment in which these galaxies live in. So what we are trying to do is, like, since we know that these properties are dependent on environment, we would like to explore how these properties can be they how do these properties trace the galaxy environment, and that is one of our aims. Then we would also like to check to what extent can we use different pass bands in luminosities as proxies to stellar mass and star formation rate. Uh, uh, because there has been many works in which people have used different bands in luminosities in, as proxy for stellar mass and SFR. So we would like to explore to what extent that is possible in galaxy clustering. Then we also wanted to explore how, if the survey limit of the sam of the the flux limit of our survey, it affects the clustering. So we will look at the results, but for that we have another tool called the marked correlation function. So it is developed from the two-point correlation function. In marked correlation function, we first assign each galaxy a mark. So what is a mark? It can be any measurable property of our interest. That is, if we want to, if we want to explore the environmental dependence of luminosity, we use luminosity as a mark. Similarly, which property that we are interested in, we use that property as a mark, and this mark is used to weight the galaxies, and then we compute the mark correlation function. And once you compute the mark correlation function, its strength shows that how strong is that property that we have used correlate with the environment. This is one estimator that we use, where W of R is the weighted correlation function, which is estimated similar to the two-point correlation function, but in weighted correlation function, we consider the properties of the galaxies, which we do not do in two-point correlation function. That is, we weight the galaxies according to their property. Then, okay, so moving on. So since we had the weighted correlation function is in the numerator, the weight that we have for a property, it enhances the significance of galaxy pair in which both the galaxies have a given property more pronounced. For example, this is the work by Skiba et al., in which they have used the luminosity as a mark, and this is the luminosity marked correlation function. Hmm, so here we can see that on small scales, it shows amplitude which is like greater than unity, which means that on small scales there are more number of galaxy pairs in which both the galaxies are strongly luminous, and this uh, goes down, the effect, the signal goes down as the scale increases, because on large scales the galaxies are like least correlated with each other. That's the reason why it goes to unity, because when Mark correlation function equal to unity, which means that both these terms are the same. That comes only when the properties that we have used are not giving they are not correlated to the environment. And yes, just like the two-point correlation function, we project the mark correlation function in practice. So you can see MP of RP is the marked correlation functions. Okay, so in our work, we have used the data from GAMA, uh, which is a spectroscopic multi-wavelength survey, and the flux limit of the gamma survey is 19.8 in R band, which is 2 magnitude fainter than SDS's main galaxy sample, which is really advantageous. And this is the sky coverage and the redshift coverage of gamma in comparison with other samples. Okay, so in this we use different galaxy properties. These are the properties that we use, that the luminosities in U, G, R, J, and K bands, then the stellar mass, star formation rate, and specific star formation rate. And we select a set of galaxy samples for the same purpose, and these are the samples we have selected. But first we will look at this sample A1, which is with the flux limit 19.8, which is the actual flux limit of the survey, and then the mass limit 9.3, and this is the distribution, and this is the result of the uh, computing correlation function and marked correlation functions, where in left panel you can see the two-point correlation function which obeys a power law with the parameters as shown here, and in the right panel you can see the marked correlation functions for the same galaxies measured using different properties, and as you can see in the legend. So we can see clearly that different properties give different weight to the correlation function, and which means that different properties are related to environment differently. So we will look into more into the marked correlation functions. Uh, for example, when we look at all the scales, the stellar mass, let's say this one, then G, R, J, and K band MCFs are above unity. These mark correlation functions are above unity, which means that on smaller scale there is a greater probability of finding galaxies which are with both the galaxies similarly stronger in these bands, which is the same result as we have observed before, that the brighter galaxies in G, R, J, and K bands, and the massive galaxies, they are more clustered than others. Now, but when it comes to U band and star formation rate, their marked correlation functions, they exhibit an opposite behavior, which is because the galaxy pairs with stronger U-band luminosity and the star formation, they are like majorly far separated. That means we won't be able to see highly star. I mean, if you look at in the denser environment, there is less probability of finding highly star forming galaxies. That is what we see here. Now, when we look at the different mark correlation functions, we see that stellar mass MCF is stronger than all other MCFs. which means stellar mass proves to be a better tracer of environment than others. And when it comes to K band, among all the luminosities, K band is the one which is stronger. And we see that the K band luminosity MCF and stellar mass MCF, they both are similarly behaving. They are near to each other, which means K band can be a good proxy of stellar mass. But if we do so, we have to be careful that we tend to miss out galaxies which are massive. So which are like close pairs of massive galaxies, evolved galaxies. Now, similar is the case with U-band luminosity. U-band can be a good uh, proxy of star formation rate, but still not a perfect one. Now, we also wanted to check if the flux limit affects our measurement. For that, we select two samples B1 and B2 with the same mass limit but different flux limit. So, and we compare their correlation mark functions and mark correlation functions. This is a redshift distribution. So, we will compare this in the next slide. Okay, so here in the left panel, you can see the 2-point correlation functions and their parameters, and we observe that they are not really affected. They agree to each other with both the samples, but their mark correlation functions are affected. You can see somewhere where this is a ratio of the mark correlation function, and they have a significant difference at subscales. We also wanted to check the same effect if we go to further brighter flux limits, and for that we have used SDSS also, and this is the samples distribution. Now these are the results from there. On the left panel, it's a 2-point correlation function where we see that all the samples, they really agree to each other. You don't see much significant difference in their clustering behavior. But when it comes to the stellar mass mark correlation function, we see that the gamma samples, that is C1, C2, C3, they are not really affected, but the SPSS samples are affected. This can be because when we have different flux limits for the same mass cut, gamma samples do not vary much from each other, but the SPSS samples vary in number. So this can be one reason why we do not see the effect in the gamma mark correlation functions. Now these are the results that we have obtained. So using mark correlation function in gamma, we observe that different galaxy properties trace the environment differently, and stellar mass proves to be a better tracer of environment than luminosity and star formation rate. Then the sample which is complete in K-band luminosity can be a good substitute for stellar mass complete sample. But in such a case, we have to be careful that we may tend to miss close pairs of evolved galaxies. Then U-band luminosity can be a good but not a perfect tracer of star formation rate. Also, we have observed that the survey flux limit imposes incompleteness, which affects our clustering measurements in stellar mass selected samples. So that's all. Thank you. And if you have any questions, please contact me. This is my email ID, and thank you very much.